The Hodgkin Huxley model, analysis of dynamic behavior of the action potential in the giant squid axon. 1. Introduction. We should primarily concentrate on neurons, but it is prudent to begin this analysis at the most fundamental level, the brain. In brain, a cell is an entity that is the smallest structural structure capable of operating independently. Neurons are a particular type of cell. These are trained primarily in sending electric signals to other neurons. There are three separate parts of the neuron that we ought to understand: the cell nucleus, the dendrite, and the axon. The electrical impulse that brings an instruction from the brain to, for example, the hand passes along a chain of neurons. 1. The nerve cell to neuron signal transfer happens at the synapse, a fluid flow region between two communicative neurons. The electrical impulse of the presynaptic neurons is translated into a chemical message in the synapse and translated again into an electronic signal in the postsynaptic neurons. 2-3. 1.1 Representations of biological neuronal model. 2.1 Membrane potential. 2.2 Nernst potential. These are the most biologically reliable ones. Different model parameters represent those biological components of the neuron. Such models illustrate how the neurons work in depth but are costly to quantify, and therefore the simulations appear to be sluggish. We model the capacity of a neuron to combine inputs and fire through a threshold. The Hodgkin-Huxley model is a neuron point design. Point neuron simulations are concerned mainly with how the neurons treat input voltage to generate or not create an action potential. The Hodgkin-Huxley method is a form of accurate description of the neuron. This model is concerned with how ion motions cause shifts in the voltage of the neurons. Therefore, to understand what this model mimics, the basic knowledge of ion changes is necessary for 2. Ionic movement. The crucial argument that Hodgkin and Huxley were able to show seemed to be that two ion forms, namely sodium, Na, and potassium, K, would adequately clarify the electrical properties of the neurons. Outside the cell, the Na+ concentration is higher than inside, so these ions are driven by diffusion into the neuron. Often, when sodium ions are drawn into the cell by electrical forces as the cell is. Figure 1, ionic movement of and. The ions also operate with two forces, diffusion and electrostatic pressure, which influence the ionic flow of the extracellular and intracellular fluid. The diffusion force pushes the ions to disperse the ion uniformly throughout the liquid, with no high or low concentration regions. Furthermore, as the intracellular fluid contains a high concentration of plus, absorption pushes these ions into the extracellular fluid. Electrostatic pressure causes the same charge ions to be repelled, whereas ions with opposite charges are attracted to each other. 4. Both cells in the body have electrical impedance or potential differences throughout inside and then outside it. Because the cell membrane differentiates inner surface from the outside, this potential variation is considered as the potential of the membrane. In scientific terms, the cell voltage is described in equation 1. Vx equals 6 VO, 1. Where is the voltage of the inner cell and is the voltage of the outer cell. It is going to change during an electrical potential. Capacitance is known as a charge kept divided by the voltage needed to hold the charge. 5. Cx equals Q/V, 2. This capacitance is believed to be continuous, i.e. not time dependent. Therefore, by taking the time derivative, we can obtain the following equation from the movement of charge across the membrane. dq dt equals Cx dV dt, 3. This formula is important to evaluate the membrane potential of the Hodgkin-Huxley model for all the work to be done on this topic. 1. The electrical potential produced by the electrochemical balance of the membrane, the equilibrium potential, can be calculated by a simple formula called the Nernst equation. Equals ln. 4. Here R is the universal gas constant, T is the absolute temperature of Kelvin, F is the fixed value of Faraday, and Z is the valence of the particle. Because three of these parameters are environmental parameters, One often comes across different formulas where these constants have been defined by their importance in the issue under discussion. 3. Hodgkin Huxley model. The Hodgkin Huxley model is one among the biological models. Abbott and Kepler, 1990, utilizes 4 differential equations to live the potential of the membrane. These 4 differential equations model the ionic activity of the brain. Hodgkin as well as Huxley carried out experiments on the giant squid axon and found 3 categories of electrons current, i.e. sodium, potassium and leakage current consisting primarily of chlorine ions. The movement of these molecules from the cellular membranes is regulated by different ion-dependent voltage mediums for sodium and potassium ions. Certain channel forms are not explicitly described with the leak current. The semi-permeable cellular membrane separates the interior of. Figure 2, simplified equivalent circuit for a small section of the giant squid axon. In Figure 2, the input current I, T, is transferred through the cell, either providing significant charge to the capacitance or leakage along the cell membrane mediums. A resistor represents each type of channel. The unspecific channel has a resistance to leakage, a resistance to the sodium channel, and a resistance to potassium channel. The concentration of the ion within the neuron varies from the one in the extracellular material by the intensive transport of the ion across the cellular membrane. Nernst potential is different from every sort of ion. The sodium, potassium, and undefined leakage channel voltages are, and respectively. The conservation of electrical charge on a membrane piece indicates that the current 9, T, added can be separated into capacitance current I that affects the condenser C and that passes across ion medium 6. 9, T, equals IC, T, plus 0.2, T, I, 5. Where 0.2, T, equals INA plus IC plus ELI. The theory of electrical circuits states that the amount of voltage shift over the capacitor is equal to the maximum current used to charge it, or 9, T, equals Cx dVx dt plus in, 6. Where the current among 3 channels is, in equals GNA asterisk Vx VNA plus GK Vx VK plus GL Vx VL. Whereas its leakage channel is defined by a voltage-dependent conductance, equals 1 slash. Because is the overall potential around the membrane and is the reversal potential across leaky channel, the voltage at the leaky channel is, dash. By applying Ohm's rule at leaky current IL equals GL, Vx VL. The time-dependent membrane current is where are reversal potentials. When this mediums are free, it transfer currents among a greater conductance. Even then, a few streams are being blocked. M, N, and H are gating aspects that are created to design the possibility that a channel will be opened at a given time. The cumulative constants of M and H handles the channels while K gates are handled by N constant is shown in equation 8. The efficient conductivity of the sodium channels is defined as 1 slash, equals, 3H where M specifies the initiation, opening, of the medium and H the termination, closing slash blocking, of the medium. Potassium conductivity is 1 slash, equals, 4 while N represents the initiation of the channel 6. The change in the gating variables is based on the following differential equations. dN dt equals nVx1n SSN Vxn dm dt equals mVx1m SSM Vxm. dH dt equals AVx1h SSN Vxh, 9. 4 voltage clamp used by Hodgkin and Huxley. In many of the studies conducted by Hodgkin and Huxley, an electrode was injected into the squid axon to keep the membrane at a fixed voltage. Figure 3 shows the calculated current flow from the axon of a giant squid through a specified region of neural membrane to calculate how ions move through the neuron membrane during an action potential 8. The voltage clamp enabled the ionic currents to be registered directly, flowing through the giant axon's axonal membrane without any subsequent membrane potential adjustments. A simple voltage clamp can iteratively calculate the membrane potential, and then adjust the membrane potential, voltage, by applying the required current to the target value. It clamps the cell membrane at the ideal voltage constant, enabling the clamp to monitor what currents are transmitted. The voltage clamp eliminated capacitance problems and created an isopotential membrane 8.5 Hodgkin Huxley model using Euler's method. The computational method of Hodgkin and Huxley was one convenient for manual computation by means of the tools at that time. The task of determining the value at a given time is an integral part of the differential equation. The difficulty with this is that the four differential equations are interrelated and therefore it is difficult to calculate the integral. Then, an approximation of the equation is used, often by the Euler method. In Euler's process, there is a parameter that is the time step dt, which, based on the values selected, which make it impossible for the model to function or make it take too long to operate. A general first-order differential equation of the form dy, t, dt equals f asterisk y, t, 10. Therefore, in the computer analysis of Hodgkin-Huxley calculations, one needs to be careful when picking a discrete time stage duration. Sensitive protection is to seek small variations in the chosen value for 7. Applying Euler's method to the membrane voltage equation. Vx, t plus dot t, equals 1 dash dot t, Vx, t, plus dot t t n a e n a plus dot t t k e k plus dot t t l k l k, 11. 6. Simulation of Hodgkin-Huxley. Each section displays the action potential along with the related plots of the time for gating parameters. Such plots were obtained by computer simulations using the forward Euler method technique with differential equations. There is a time stage of 1s. The HH model simulated its action potential with an applied stimulus from t equals 0 ms to 2 milliseconds. The and conductances can change with time, since these correspond to the Na and K channel opening and closing shown in Figure 4.5. Figure 4, the action potential generated by an exterior pulse width. The velocity constants and SS can be determined using MATLAB technique as the function of the cell voltage V and the temperature T parameters V, in MV, and temperature T, in Celsius, are transferred to the operations. Figure 5 shows the equilibrium constants at T equals 6.3. 8. Figure 5, figures of the equilibrium constants A and SS at T equals 6.3. Figure 6 shows the reaction of M, H, and N to the step-in potential 4. In Figure 7, it shows how the difference in the gate factors, the conductances, and the current densities of the voltage clamp added to the axon. Because the step variable is increased, the variables of gates, N, M, H, then the conductances, and, then the current densities are calculated for each. 7. Conclusion. Generating and propagating the action potential deals with the interaction of the conductance of sodium and potassium voltage dependence. In the original Hodgkin and Huxley formulations, important assumptions were made about how the voltage can affect the conductance. The key goal is to provide a comprehensive physical account of all circumstances and kinetic variations between the channel molecule states. The model suggested is beneficial for study of neuronal coding involving neuronal networks.